Action. Or maybe not.
No, not yet.
Okay, yeah. I'll end it. End. Wow, Ella, you look so happy.
Good job, Ella.
You got it, Ella.
Where's my assignment? I don't know if I said different.
It's over here.
Did I say different?
If you
Probably.
Sorry. Ow.
okay, so here's the second to the last big topic that we have to cover, and that is pressure volume graphs and how they play out and what we can figure out from them. So let's start kind of at the beginning. So I'm going to give you a sample of a gas. It's going to contain 0.1 moles, okay? Not entire mole, just 0.1. Temperature is going to be 20 degrees Celsius, about room temperature. The volume is 0.1 cubic meters, which would be about like yay, okay? And I want to find the pressure that's in, I want to find the pressure of the gas in the flask. So what can you start with?
PV equals nRT.
PV equals nRT, right? Now, what does that temperature have to be in?
Kelvin.
Kelvin. Never in Fahrenheit, never in Celsius. So, how am I going to get from 20 degrees Celsius into Kelvin?
Add 273.
Which gets me 293 Kelvin. So, I'm trying to find the pressure. So, I'm going to go inert over my volume is going to equal my pressure. Now, it's handy if you kind of visualize how a pressure sensor works. So if you model this baseball as being like a nitrogen oxygen cell gas, okay? So when it hits, it's going to hit and it's going to bounce back. And obviously the faster it's going, the more force that's going to take. So if it's just a little bit just like this, that's different than something like that. So what the pressure sensor basically does is it sits there and goes, okay, I'm going to have a certain number of collisions. Based upon those certain number of collisions, we as a species have said, hey, that's going to be 1 atmosphere, or that's going to be 14.7 psi, or that's going to be 760 millimeters of mercury, whatever that's going to be. So we've arbitrarily picked all these different scales. So, but if you remember, the pressure sensors work by measuring collisions with gas particles, and they bounce off, okay? So, in this case, I got 0.1 moles, right? I'm going to use that ideal gas law constant of 8.314 joules per mole Kelvin. My temperature is 293 Kelvin. So that gets rid of my moles, that gets rid of my Kelvin. And then I divide by that volume of 0.1. My pen is being stupid today. Cubic meters, okay? So that's basically going to cancel out. So somebody take 8.314 times 293.
$2,436.
That doesn't sound right.
What'd you get?
2,436.
That's what I got too.
What'd you get? 8.314 times 293?
It's like 8
Times 0.1.
8 times 300.
Divided by 0.1.
Okay, that's fine. 2 point what?
4.
Oh, okay, all right. That's okay. Times 10 to the third newtons per square meter. Okay? So on this graph of pressure and volume, we've got a volume of 0.1. We're going to come over here, and that's going to be 2.44 times 10 to the third newtons per square meter. Okay? Now, that's a lot less than normal atmospheric pressure. Normal atmospheric pressure would be like 1.01 times 10 to the fifth. Okay? So this is like 100 times less than normal pressure. Okay? But here's what you have to realize on these pressure volume graphs. it's a two-dimensional graph where you have pressure and volume, but in reality, there's a third component that you can always find. Because if you know the pressure and if you know the volume, assuming that you know the number of moles, you can always find a third point of information, which is going to be the temperature, because PV equals nRT. So you're always going to know a pressure, you're going to know a volume, but then you can work it out, and you can also find the temperature as well at any point on here. Now, on the back of the lecture notes that I gave you all yesterday, we're going to deal with 3 different processes. I'll start with the words ISO. ISO meaning similar or the same. So we're going to do isothermal, which means that the temperature is going to stay the same. We're going to do isobaric, which means that the pressure stays the same. And then we're going to do isovolumetric, which means that the volume stays the same. So those are going to be the 3 processes that we're going to do. I'll start with ISO. ISO meaning similar. So if you ever study weather, you look at maps and you look at what's called isobars. Isobars are lines of equal pressure. You can look at isotherms on a map. Those would be lines of equal temperature. So iso something means similar. So on this graph, you can show some different things. You can show expansions where the volume gets bigger. You can show contractions where the volume gets smaller. You can see where the pressure is going to change. You can see where the volume is going to change. Now, let's just start with some basic ideas. So let's say that you have a pressure volume graph and pressure volume. And let's just say that it's a horizontal line, okay? Going across like this. So this is going to be some number of newtons per square meter, and this is going to be volume in cubic meters. Let's just say it's a horizontal line. Could you find the area underneath that line? Yes. Yeah. So you're going to take newtons per square meter times cubic meters, right? Go with this. These cancel out. You get Newton meters, otherwise known as joules, right? So here's the first thing that you have to understand. The area underneath any line on a pressure volume graph is going to represent work, because the units work out to be joules. So here's the simple idea. So I've got a syringe like this, okay? And I'm going to push, never mind my blue fingernails, copper sulfate spilled this morning in my chemistry 1 class. So, it's really not radioactive or anything like that. Okay, my hands are glowing in the dark. No, it's okay. So, if I take this syringe and I push this, did I just do work?
Yes.
Why? I exerted a force over a distance. Now, if I just hold this thing, am I doing work? No. Why?
No change.
No force over distance, right? So this is going to be important. If work is going to be done on a gas or by a gas, the volume has to change. Okay? That's rule number 1. So what we're going to do first is we're going to go through the most complicated of the 3 isos, okay? Which is isothermal. That's the most complicated. The other ones are pretty simple after you figure out the isothermal one. So that's why I'm going to start with the most complicated one, and then I'll end up with the simplest one. Okay. So what we're going to do is we're going to go to this graph. We're going to say, okay, I'm going to start here, and I know the initial volume is 0.1 cubic meters. And I've got that pressure of 2,440 pascals. So what I want to do is I want to expand this gas on what we call an isothermal. You'll see why this is a curved line in just a second. So I'm going to expand that out to 0.5 cubic meters. So visualize this, okay? This is why you all intuitively understand gas laws. I just have to convince you that you do. So here I've got a gas. It's at 5. Pick a point. So I'm going to pull back on that syringe until it goes to 15. When I did that, what do you think would happen to the pressure inside that syringe? Decrease. Okay, if you make the analogy with second graders, right? God forbid I'm teaching a class of second graders. Okay? God forbid. And there's a certain amount of pressure because the little ankle biters are running into my legs, right? And that's what's creating pressure, right? And I'm going, I can't handle this, I need my space. So I'm going to take the little ankle biters from the classroom and I'm going to take them down to the gymnasium, okay? Now, what's going to be important in this story is that we're not going to change the number of Skittles that the kids have, okay? Because the temperature is going to stay the same. So what's going to happen, when I go from the classroom down to the gymnasium, what's going to happen to the number of collisions with my ankles?
Less.
It's going to drop, right? So I'm going to have less pressure, not because the kids have less energy. I'm going to have less pressure because there's more space for the kids to run around. Therefore, I won't have as many collisions. My pressure is going to drop, okay? Now, when you look at this in terms of PV equaling nRT, so we're going to look at this, PV equals nRT. So the inert side of this is going to stay the same because I'm not going to change the number of kids in the classroom, I'm not going to change the gas law constant, and I'm not going to change the temperature, okay? So the inert side is going to stay the same. It's going to stay the same. Boom, it's fixed value. So what I did is I made the volume get bigger. So as the volume gets bigger, with the same inert, what has to happen to the pressure? It has to become smaller, okay? Because I want the same inert over there. Same inert, volume gets bigger, pressure gets smaller. Now, what I want to do is I want to calculate that new pressure. So do I have enough information to calculate that new pressure? Assuming that my pen was right, which it doesn't want to do. I really hate my pen today.
Another new volume.
Did you drop it again?
But you know how many times I've dropped this thing?
A lot.
A lot. I almost need to like training wheels.
Get a bracelet.
There we go.
Put it in the
Okay.
net underneath.
Yeah,
Oh,
put a
yeah.
bracelet. Okay. So could I go back to PV equals nRT and find the new pressure?
Yes.
Yeah. I still got 0.1 moles. I've still got my R value, 8.314. I'm still at the same temperature. This is going to be critical. I'm still at the same temperature of 293. But now my volume is going to be 0.5.
Can
Okay?
you not use the P1V1
Or
equation?
you could use P1V1 over T1 equals P2V. You could do that too.
Oh, okay.
Okay? It's whatever works for you. But whatever, somebody give me this number. So 0.8314 times 293 divided by 0.5. Or you can take whatever. What do you get? It's going to be a lot smaller.
487.
487? Newtons per square meter. So this thing has dropped like a rock. So now this pressure is all the way down to 487. Okay? So now we're all the way down here to 487 newtons per square meter. So we went from basically 4,400 down to 487, okay? Because we increased that volume so much. Fewer collisions, same temperature. Okay, now, bank that. We're going to circle back to this. So on your equation sheet, on the back side, you have some relevant equations dealing with gas laws, okay? So we've already talked about the one that PV equals nRT. So now we're going to talk about these middle ones where it has Q plus W equaling delta U, which also equals 3/2 NR delta T. So let's talk about what this is. So let's talk about Q first. Q is a transfer of thermal energy, okay? So let's say, for example, I grab a hold of yonder thermometer and I hold on to it, okay? So as soon as I hold on to this, the temperature in the thermometer begins to go up. Because what's happening is that I'm transferring thermal energy from my hand into the thermometer, okay? So there's going to be a transfer of energy from where it's hot to where it's not. Now, if I took this and put it in an ice bath, what would happen?
Energy.
Temperature would
Flow out.
flow out. So Q can be positive or negative depending upon the direction of the flow of energy. So if this is your system, okay, it's a thermometer, it's a test tube, whatever it is. If energy is flowing in, you have a positive Q, because that energy is going to go into increasing the thermal energy of the system. If energy is flowing out of the system, oddly enough, you have a negative Q value. So if energy flows in, positive Q, energy flows out, it's negative Q. That's the simple one, okay? Now, obviously, if there's no change in temperature, hey, Q is just going to be a zero value, okay? And oddly enough, what units do you think Q is going to be measured in? Joules. We did this calculation. Q equals MC delta T. You could calculate how much energy was absorbed by the water, how much energy it took to melt the ice, okay? That's just that basic Q value, okay? Not a big deal. Now, the work gets a little sketchy. So work can be one of two things. The work can do either make the volume get bigger, or the work can make the volume get smaller, okay? Those are your two options. So if the volume gets bigger, okay, if you increase the volume and that expands, so if you increase the volume, that's going to be negative work. So if I take this syringe and I compress it, I'm making the volume smaller, okay? That's going to be negative work. But if I compress it and then let go of it and then that pushes back, then the gas is doing work on the surroundings and that work would be a positive value. So if the volume is getting bigger, that's negative work. If the volume is getting smaller, if you're decreasing the volume, that's going to be positive work. And you'll see that why that works later on mathematically. So, Q can be positive or negative, work can be positive or negative. Now, let's talk about delta U. So delta U is probably one of the most important concepts in thermodynamics because it represents the sum total of all of the energy in a system, okay? But here's the problem. We don't have any, there's no such thing as a delta U probe. We don't, there's no, it isn't like, oh, hey, go get the delta U probe and we'll hook it up into the LabQuest and we'll measure delta U, okay? So here's the anomaly about delta U. It's one of the most important concepts in all of thermodynamics. And there's no way to measure it directly, okay? You can't. Because this is a sum total. So imagine, here's the best analogy that I can give. I walk in to a second grade class, God forbid, and you got Timmy, you got one Timmy bouncing off the walls, you got another Timmy, you know, spinning on a wheel, you got another Timmy just kind of sitting there going, okay? And you got all these kids. Some of them are doing jumping jacks, some are doing somersaults, okay? Some are just walking around, okay? One kid's hanging from the ceiling, got some potential energy, whatever, okay? So if I could measure all of that energy, all of that combined energy, okay, that's what U is representing. It's the sum total of all of the systems. But we're really not even concerned about that. What we're worried about is the change in U, okay? So here's the best analogy that I can give. Riley walks in, she's all excited. She goes, Mr. Burkett, I found $20. Good, cool, right? She found a $20 bill. Walked along, found a $20 bill. Now, all I know is that's how much her account has changed. It's $20. Now, she might have $5 in her bank account. She might have $2 million in her bank account. Doesn't matter. All I know is that her account changed by $20. What the baseline was in her bank account, don't know, don't care. All I know is that I'm happy for Riley because her change was 20 bucks. I don't know where she was to begin with, doesn't matter. I'm just happy for her because she found $20, okay? So when we talk about delta U, we're not talking about, we don't know what the baselines are. All we can figure out is how they're going to change. Now, delta U equals two things. It equals the sum of the energy and the work. That's one option. The other option is, this comes from a statistical model, is that it also equals 3/2 NR delta T. N is going to be the number of moles. R is your ideal gas law constant. Now, notice that this is change in temperature. Okay? It's not the temperature. It's the change in temperature. So if there's no change in temperature, guess what your delta U value is going to be? Goose egg. It's goose egg. Riley walks into class, find any money today? Nope. Okay, cool. Her money didn't change. Okay? I'm not saying she's not in class. I'm not saying she doesn't have energy. I'm just saying there's no delta U. Okay? Makes sense. So obviously, if my change in temperature is a positive value, my final temperature is higher than my initial temperature, what's going to be the sign of delta U? Positive. Oh, I put a lot of energy into the system. Okay? So you can think of the temperature as being Skittles. Okay? So if I give Skittles to the kids, wow, I like Skittles! Right? They're going to be very excited. They're going to be very hyper. And that energy in the room is going to increase. Okay? The other option is, she goes, I can't today. Timmy, I cannot deal with you today. Timmy, give me your Skittles. Timmy's going to be crestfallen. Okay? So he's going to lose energy because we took Skittles away. Okay? Got the idea? Yes?
Are what's Q and W like independent of each other? So like
Yes.
their negative signs don't
completely
have to. Okay.
independent of each other. You could have two positives, you could have two negatives, positive and a negative and a positive.
Okay. So
Okay.
they don't affect each other at all.
Nope, nothing to do with each other whatsoever.
Okay.
Now, so let's look at, oddly enough, the units. So if you look at delta U equaling 3/2 NR delta T. So N is going to be the number of moles. That's your gas law constant, joules per mole Kelvin. And this is going to be your change in temperature in Kelvin. Kelvins cancel out, moles cancel out, you're left with joules, which is the same thing Q is going to be measured in, which is the same thing work is going to be measured in. Okay? So I can't have one side of the equation producing joules and the other side producing newtons. Okay? It can't work. Got this idea? Got it. Okay. Now, on the back side of those lecture notes, okay, let me see those lecture notes.
Which one?
The one's that sheet right there. That one. Okay, so on this back side, on this isothermal one, I've got this handy dandy little equation, which is going to be important. You have nRT, natural log of VI over VF. Thank you. So let's talk about this. So here's the problem with isothermals when you have a pressure volume. They're curved lines, okay? They're curved lines because they're inverse relationships of each other. Pressure goes up, volume goes down, okay? So when we try and find that area underneath there, this is something that we haven't experienced before. Because all the other areas that we've dealt with have either been triangles or rectangles, okay? Something similar. Well, this is a curved line. And the only way you can find the area underneath the curved line is to use calculus, because of the fact that you have like infinitely number of smaller rectangles. So this equation comes from calculus. Don't worry about where it comes from. You just have to know how to use it. Now, let's have a quick refresher of natural logs, okay? Quick refresher of natural logs. Anybody remember what the natural log of 1 is? 0. Okay, this is going to be important. So the natural log of 1 is 0. So this is where this fits into a bigger picture. This is volume initial over volume final. So if my initial volume is the same as my final volume, I'm taking the natural log of 1. 1 times anything is going to get you, or excuse me, 0 times anything is going to get you 0. So if my two volumes are the same, I'm taking the natural log of 1. That is a numeric value of 0. I'm not going to do any work. Okay? So work is only going to be done if the volumes change. Okay? Now, what we're going to look at on our example, we've got N being 0.1 moles. We got 8.314 joules per mole Kelvin. My temperature was 293 Kelvin. And then the natural log of my initial volume, and my initial volume was 0.1 cubic meters, and my final volume is going to be 0.5 cubic meters. Now, before you touch the calculator, do not touch the calculator, step away from the calculator. Okay? Step away from the calculator. We're going to be taking the natural log of basically 1/5. 1/5 is the same as 0.2. So does anybody remember what's the sign of the value of a natural log of a value less than 1? Is it positive or negative?
Negative?
Negative. Okay, so the natural log of any value that's less than 1 is going to be a negative value. So that's how I know when I calculate this work, I'm going to end up with a negative value because of the fact that my final volume, okay, is bigger than my initial volume, and that's why I said work is going to be a negative value. Okay? So now that we have this, so somebody take 0.1 times 8.314 times 293 times the natural log of basically 0.2. So what'd you get? Oh, I like that.
Agreed.
Joules. Okay? So what that represents is the area underneath this line. Okay, so that negative 392 represents the numeric value underneath that curve. Okay? Everybody hip with this. Now, last and final step. Okay? Last and final step. So we just found work to be negative 392 joules. Delta U is going to equal what? Nope. Nope. Nope.
Plus work.
3/2
E plus work.
NR delta T. What's the value of my delta U?
It's that. Oh,
No, no, no.
It's this. Are you talking about for constant?
For this one that we're working
Zero.
right now.
It's 0.
0 why?
There's no change in temperature.
There's no change in temperature.
Wait,
So
what?
delta U
bottom.
in this situation is going to be 0. Because by isothermal, by that definition, the temperature doesn't change. Okay? So my delta U is going to equal OJ. No work is, the overall change in energy is going to be 0. I'm not saying things aren't going to happen. I'm just saying the overall delta U is going to be 0 because we're not changing the number of Skittles that the kids have.
Then
Okay?
why would they have that equipment?
So boy.
Huh?
Does that mean Q is 392 positive?
Yes.
Oh, okay.
So, because delta U equals 0, which also equals Q plus W. So, if my Q is going to add up to W to get 0, and my work is negative 392 joules, guess what? My Q value is going to be 392 joules. I don't know what I'm trying to write in. So those add up equal to 0. So here's what this would actually look like. Okay? This is what this would actually look like. You'd have to have a syringe or something like this where the volume can change. Okay? I can't do this like in a sealed up test tube. Okay? Because I can't change the volume. I can't do it in a sealed pop can. Can't do it in a cup. Okay? Volume has to be able to change, right? It's the first thing that has to happen. So what would happen is that the volume is going to get bigger. So what you would see is you would see that stopper on that syringe move. Okay, you would increase the volume of the system. The other thing that would have to happen is that you would have to allow energy to flow into the system, okay, from an outside source. Typically that might be like the lab you guys are going to do tomorrow. That's going to be a hot water bath, okay? You're going to put, well, Monday. I forgot today's Friday. So you're going to put, so what you would do is you would put this in a hot water bath. And it would have to be a material that allows energy to flow very easily. Like you won't do this lab like in a well-insulated thermos. What's the idea of the Yetis and all of that? What's the appeal of the Yetis? What are they designed to do?
Don't change temperature.
Yeah, they're designed to minimize the change in temperature. They're designed to minimize a heat flow across a gradient. Okay, it keeps hot things hot and it keeps cold things cold. Right? So you don't want to try and do an isothermal compression or expansion with a Yeti cooler. Number one, you can't change the volume. Number two, you're not going to allow that energy to flow in and out. So you want to do this typically like with a syringe, where it's very thin, so energy can flow in and out of it, and you can change the volume. Okay? So here's the best analogy that I can give. All right? So let's say upon my passing, they're reading my will, and I'm going to bequeath to Dime $150,000. Okay? Dime gets $150K, right? But
Is that only 150,000?
oh, my
I
bad.
don't have a good sense of money. Okay? We were making fun of her because, yeah.
Okay. Dime gets $150,000. And everybody goes, and Dime's going, this is cool. But I said, but, I have a different kind of will. So,
What's a different kind of will? Oh, that's funny.
that's really all that matters. Okay. So, the caveat is, he can't keep any of the money. He has to spend the money to do work. He has to make the world a better place. Okay? He has to feed the hungry. He has to put solar panels on. He has to build playgrounds at schools. Okay? He has to buy books. So, I'm going to leave him $150,000. But you don't get to keep any of it. Okay? So, this is a situation where I put energy into a syringe, but the syringe doesn't keep the energy. What happens is that we're going to do work. We're going to make the volume get bigger. So that would be like the room mom showing up and going, hey kids, everybody get Skittles. And Timmy comes out and he goes, I love Skittles. And he's very happy, right? But the teacher's going, whoa, I can't deal with you, Timmy. We got to find something for you to do with that energy. Timmy, go push on the walls. So all the kids are going to go push on the walls of the classroom, and they're going to make the walls of the classroom get bigger. So that way the overall temperature of the Timmies remain the same. Okay? Because if we just give Skittles to Timmy, and he has nothing to do with that, he doesn't have a job to do, he doesn't have work, bad things are going to happen. Okay? So, by virtue of the fact that these classrooms can move, we can move the walls, it's like, kids, you're going to get Skittles. But, you have to do work. You've got to push on the walls. That's what's going to happen there. Got that idea? Okay. Now, kind of a dramatic way to show this. So what this is known as a fire syringe. Okay. So I'm going to take a little piece of cotton.
Ooh, I love this one.
Ooh,
Oh, is this where it goes?
kind of. Put that there.
I can't go with you because Wyatt was staying for like an hour. And
Now,
he
so
needs
let's
to go.
chit chat.
He's going
So I'm going to take this syringe and let's just make some observations. So if I push this down and let go of it,
Oh.
I thought it was gonna light
it goes back up, right?
Yeah, that was cool.
So what does that tell you about nature in terms of a compressed gas? Does it like the compression or not?
No, we don't like pressure.
Don't like it. So that would be like me confining all of you into a small space, right?
Right.
And you all going, oh, this is not cool, okay? So as soon as I change the system, you all are going to go back to this environment, right? Where you all are spread out.
Turn into Timmy.
So, but if you think about it though, it's pretty cool what's happening inside of here. So you only have these particles pushing on a very, very small area of that syringe. So when I push that down, number one, this is a heavy steel syringe, okay? So gravity is pulling down on this thing, right? Gravity is trying to keep this thing down, okay? And it's pushing against the weight of gravity, which is pulling it down. It's also pushing against the atmospheric pressure on the top of it. So those little gas particles in there, those nitrogen and oxygen molecules, they're doing something pretty cool, right? So I compress it, it doesn't like it, they go, rage against the man. Like, you can't keep me down, okay? So it pushes back up, so it's like, I gotta have my space, okay? Back off me, big man. And so it pushes that back up. So here's what's gonna be important. Obviously, if I compress you all, or if I compress the gas, your internal energy is going to go up because you don't like that system. You're going to be going like, okay? You are not going to be happy. But if I do this slowly, if I push this down slowly, nothing really dramatic happens. I let go of it, and it goes back up. Particles don't like it. It costs them energy. The volume is going to get bigger. Just like yesterday when you blow in your hand, and you pucker it, it feels cooler because that gas is expanding and it costs it energy. Now I'm going to do the same thing, but now I'm going to push down really, really quickly. Okay? So focus on the bottom and hopefully this works. Okay, so here we go. Ah, hold on, I missed. Oh, back
light
off.
on fire.
Did it not?
No.
Hold on. I'm going to try to
Get a really big piece.
No,
I think it's supposed to light on fire.
it is.
Is it loud?
No, it's not. It's more of a flash. Okay.
Oh, wait. Okay.
Wait!
Sorry, I have to reframe the camera.
Okay. Are we reframed?
Yeah.
Okay, let's try this again.
Oh, that's awkward.
Did it do it?
No.
Is there already a piece in there?
Hold on. It did a little bit, just not. Hold on.
Today.
I know. It's a bad physics day.
Yeah, stop.
Today's Fire Day?
No, Friday. Not Friday.
Oh.
Okay, here we go.
It's Friday.
Oh, wow.
Okay? All right, I'll do it again.
That's so cool.
That's energy.
So if you look at it, it's actually singed
It smells good.
around the edges.
That's so.
Can you start a fire like that?
Yeah. Well, but it's just a tiny little fire. The problem is how do you sustain it? Because the problem is you consume the oxygen that's in there really, really quickly.
Be on your roof jumping. Is that why like flour mills used to explode?
Well, no. That's just because they have very, very flammable materials in the air. Okay. Okay, so let's try it again.
Tiny.
Tiny?
The first one was better. I don't think you can beat it.
Hold on.
It's at the bottom of it. It's at the, on the.
You got.
Oops.
You guys didn't. Ella and I were blue.
We can match every day.
I was thinking of wearing black on black.
So was I, but then I just like not do it.
Yeah. I felt like
I
I wanted to
couldn't
be
find a,
happy.
I couldn't find a black jacket, so I had to wear a white jacket.
I actually.
Yeah.
Never
I
match.
guarantee you. Take a flanker.
It's a good day to do some physics.
Okay, here, try one more.
Yes, we have to do it again.
It's gonna be dizzy.
Look at the look. Do you see the look you're getting?
That was the best one.
Now he's gonna do it different.
One more.
And they're still smoking.
Uno más.
I believe.
You resupply the oxygen.
My only complaint.
So it looks like he doesn't want to be there.
What pose are you doing?
Okay. What, are we filming?
You can
Watch
Yes.
it not work now.
anyway.
Okay, you ready?
Yes. Oh dear. That was on fire.
That was on fire. Okay. So, here's the cool thing about this. So, we caused that cotton to catch on fire, and actually, if you look at it, it's actually singed, okay? But yet there was no flame. So, this is where you talk about this delta U, this change in internal energy. So when I compressed it so rapidly, basically I didn't give a chance for that thermal energy to escape across that barrier. So all that energy stayed within that system. And that gas got so compressed so rapidly that it was able to catch that on fire. So this is how diesel engines work compared to gasoline engines, okay? This is the principle how diesel engines work. Diesel engines work by a very, very high compression rate. So what they do is they get a mist of diesel fuel mixed with oxygen, and when that cylinder compresses, that act of compressing it is what makes the diesel fuel catch fire, and then it just does exactly what happened with that piston. That it expands, it burns, and it pushes that piston out, boom, your car moves down the road, okay, whether it's a gas engine or diesel engine. Gasoline engines use a spark plug to ignite it. Diesel engines use compression to ignite it. So that's how they work. Okay, so here's what we've got. So we're going to do a quick little summary here, okay? So on a pressure volume graph, if you're going to have a line that you all can't see, here we go, pressure volume. So this is going to be isothermal. So delta U is going to equal 0 because the temperature is going to stay the same. And if we're going into an expansion, so in this situation we're increasing the volume, okay, because we're making it bigger, right? So what's going to happen is that your work is going to be a negative number because the volume's getting bigger. Your Q is going to be a positive number, and these two values are going to be equal and so that they add up to 0. Okay? So what's going to happen is that you're going to take a syringe, you put it in a hot water bath, it's going to take in that energy, and then you would see that volume expand. So what would happen is that we can only measure certain macroscopic quantities. One of those is pressure, one of those is temperature. So what would happen is that you would have a pressure sensor inside this syringe, and it measures how many collisions there are. So when you do this, if you monitor pressure, you would see the pressure go down. But if you had a temperature probe in there, you would see the temperature probe read the same value all the time. Okay? It wouldn't change, it would read the same value. But you would see the pressure gauge go down, you would see the volume get bigger, but you would see no change in temperature. Now, if you reverse the process, okay, so let's say I did this expansion, Now I want to do the reverse. Now I want to get this thing back to that point. So, look at nRT. Let's talk about the work. Work is still going to equal nRT times the natural log of VI over VF. Now, an interesting thing is going to happen. I'm going to take the natural log of my initial volume, which is 0.5 cubic meters, divided by 0.1 cubic meters, times the same N in the R. So what do you think, what's the only thing that's going to change in terms of work? Still going to be the exact same value, because now I'm taking the natural log of 5, basically. So when I take the natural log of 5, I'll get a positive value. So if I do a compression, it's still going to be the same amount of work, but now it's going to be a positive 392. So what you would see is that you would see the volume becoming smaller. So you can see that syringe shrinking. So I would have a positive 392 as my work, or joules, 392 joules. So how much energy would I have to take out of it?
392.
I'd have to remove 392 joules. So how could I remove energy from this syringe? What could I do?
Q, thermal energy or something.
What'd you say?
Oh,
Yeah, put it in an ice bath. If I put this thing in an ice bath, that energy is going to flow out. If you've ever jumped in cold water, okay, what happens? Your energy rapidly flows out of your body, okay, right? Because water is such a good conductor of energy to take that out. So if air at 32 degrees isn't so bad. You jump into water at 32 degrees, bad things are going to happen really, really rapidly, because that energy is going to flow out very, very rapidly. So if I put this in a cold water bath, what you would see is that you would see energy flowing out, and you would see the volume getting smaller. Okay, stop that, stand up, take a stretch. Okay, most complicated one.
oh dear.
And this is what we call an isobaric expansion, meaning I want to keep the same pressure. So visualize this. Here's the syringe. We've already figured this out. We know that this thing is at 293 Kelvin. Okay? That's my temperature. We're at 0.1, and now we're going to still go through the exact same change in volume. We're going to go from 0.1 to 0.5. But now we're going to keep the pressure the same. Okay? So now we're going to keep the pressure the same. So if you look at PV equaling nRT, all right, start with that idea.
Jeez.
That was loud. Speaking of pressure. So, here's the deal. As we go across, the pressure is going to stay the same. True?
True.
True. By definition, isobaric, pressure stays the same. What's happening to the volume? Perhaps it's getting bigger?
Yes, sir.
Volume's getting bigger. True?
Sam's gonna get in trouble.
What are we going to do with N and R?
Keep it constant.
Constant. Same number of moles, same idea of gas law, constant. So if the pressure is staying the same, and the volume is getting bigger, what has to happen to the temperature?
Oh, temperature must get smaller.
Temperature must get
I mean bigger. That's what I mean.
bigger. Okay? So what we're going to see is an increase in the temperature of this system. Okay? Got this. Now, we have the capacity to calculate that new temperature, right? So if we take PV over NR, I can get that new temperature. So the pressure is going to be 2.44 times 10 to the third newtons per square meter. My volume is going to be 0.5 cubic meters. Moles is still 0.1. And R is still 8.314 joules per mole Kelvin. So somebody take that 2440 times 0.5 divided by 0.1 and 8.314. What'd you get?
1.47 times 10 to the third.
So 1470 Kelvin. So look what happened to the temperature. Okay, we went from room temperature, basically 20 degrees Celsius, all the way up to, which is like 293, all the way up to 1470. So our temperature is increased by almost like 1,000 Kelvin, right? So this is a pretty big temperature change. So this is going to be my new temperature. So here's the question. What is my value of delta U now not going to equal?
0.
Why?
Because
Change in temperature.
We changed the temperature, right?
Yes, sir.
Well, do we know the initial temperature?
Yeah.
We know the final temperature now.
Yeah.
Do we know N?
Yes.
So we can find delta U, right? So we can sit here and go, okay, delta U equals NR, or 3/2 NR delta T. So we're going to have 3/2 of 0.1 moles times 8.314 joules per mole Kelvin. And then we got 1470 minus, what was the initial temperature? 293? 293 Kelvin. So let me know what you get.
Oh, would you know?
1467.
That's what I got today.
1,467?
Actually, 68 is rounded up.
68? Positive or negative?
Positive.
Positive. So what that means, and again, we have no delta U probes, but what we can measure is temperature. So we can measure the initial temperature, we can measure the final temperature, and we can measure the atmospheric pressure. And as long as that pressure stays the same, and the temperature goes up, we can measure delta U. Now we need to look at work. So here's the deal with work. So if it's isothermal, you're finding the area underneath a curved line. And that's why we have to use that calculus and we have to use natural logs. Okay? But this looks suspiciously like a rectangle. Oh, that's length times width. Okay? So if it's an isobaric line, we can treat it as a rectangle. Because we're going to know the height, right? We know the pressure. And we don't know the change in volume, which is the base. So we can just use length times width. Now, to make sure that the signs stay constant, on your sheet you have this. Work equals negative P delta V. That negative sign is there so that we're consistent in terms of the sign of work being positive or negative if it's expanding or contracting. So in this situation, my constant pressure was negative 244 times 10 to the third newtons per square meter. Now, this is going to be volume changes just like anything you've done before. Final minus initial. So my final volume is 0.5 cubic meters minus 0.1 cubic meters. Okay? So look what happens. My delta V is a positive value. But that negative sign out in front makes it work out to be a negative value for my work. So what do you get when you did this?
Negative 976.
Negative 976 joules. Now, here's the question. Why couldn't I use this equation here to do the isothermal work? Why couldn't I use work equals negative P delta V on my isothermal line?
Because you don't constant pressure.
Yeah, I don't have constant pressure, okay? If I tried to use work equals negative P on that isothermal line, it's like, which pressure do I use? Because it's continuously changing, okay? Now, just like I can't use work equals nRT, natural log of VI over VF. Why can't I use that? I can't use this one on an isobaric line. Why?
Because temperature is not constant.
Temperature isn't constant. I don't know what temperature I have to use. Okay? So this is why we have two distinct ways to calculate work. One is an isobaric line, and it's negative P delta V, because it's a rectangle, but the temperature is changing. The other one is the area underneath the curve, and we use calculus to do that, because it's the area underneath the curve, but the pressure is changing. Now, interesting question. Which one takes more work? To do an isothermal expansion or to do an isobaric expansion? Why?
Because it's the whole rectangle and not
Yeah, it's a bigger area. Look at it. It's a bigger area. So it takes more work to do an isobaric expansion than it does to do an isothermal. Now, here's what this would look like. We just found the work, right? We found that work to be, well, negative 976. We know our delta U, right? So delta U equals Q plus W. True? Good with this. Our delta U value was, what was that, 1468?
Yeah.
My work value was negative 976. So can I figure out what my Q value is?
Yeah.
Yes, what am I going to do?
Add 976.
Add that 976, so what do you get as the Q value?
It's like
444.
2000 what?
444.
So here's what this means if we go with the dime analogy, okay? I'm going to, in my will, I'm going to leave dime $2,444. Okay, that's how much I'm going to leave him. I'm going to make him spend $976 of that to do work, okay? He gets to keep the difference. So this is how much his bank account is going to change. So I'm going to leave him $2,444. He has to spend $976 of it to feed the hungry, whatever, okay? He gets to keep $1,468, okay? Cool with that. Now, last one is the simplest one. Let's say that I take this line and move it straight down. If I move the line straight down, how much work is done?
Nothing.
No work is done. Why?
Because line doesn't have area.
Yeah, there's no change in volume, right? So on an isovolumetric, guess what?
0.
No work is done. So that means that delta U is going to be the same as your Q value. So whatever energy you dump in is how much. That would be like me leaving dime $1,000 and he just keeps it all. He doesn't have to do any work with it. Okay. So let me hand out the assignment. Make sure on this assignment that you have that physical constant sheet because you're going to need values for specific heat, latent heat of fusion, latent heat of vaporization. So when you get to, like for example, question number 1. So food calories are measured based upon how much energy that you get out of it. So up at the top, I've got some handy dandy conversions. So when I typed this problem up, I was literally eating an almond joy. And if you look at an almond joy, it says it contains 230 calories with an uppercase C. So when a calorie was first defined as a lowercase c calorie was the energy that it took to take 1 gram of water and change it 1 degree Celsius. Okay, that was how a calorie was first defined. 1 gram of water, 1 degree Celsius. So here's the problem, though, with marketing, is that when they actually began to figure out the calories in food, they were getting huge numbers if you defined it as being a lowercase c. Like in a lowercase c, an almond joy would have 230,000 lowercase c calories. And the marketing to people going, this is going to be a nightmare. Man, we can't be telling people that it has 230,000 calories on it. This sucks, okay? So they said, what can we do? They said, oh, we'll lop off 3 zeros, and then we'll make it as an uppercase C, okay? People don't mind, oh, 230 calories, it's not so bad, right? 230,000 calories, oh my God, oh, that's horrible, okay? So when you look at food, and it has calories, if you pay attention on the calorie count, it will say an uppercase C, not a lowercase c. So, we as humans are about 25% efficient. What that means is if you consume 100 calories, you only functionally get to use 25 of those calories. So that's going to be the basis of question number 1. When you get to question number 8, I tell you, you're going to have 5 different calculations of Q. You've got a warm ice, melt ice, warm water, boil water, warm steam. Okay, so you can have 5 different calculations of Q, and then you have a bunch of questions relating to what we talked about today. So, all right.
Wait, what is it?
Good
Warm
luck.
ice?